from Taiwan, please.
Good morning, ladies and gentlemen. My name is俊豪学长. I'm a graduate student from Chongqing University in Taiwan. I'm honored to be here to present our study. The topic of our study is evaluating the novel methods on the species distribution modeling in complex forests. Chongqing University is located in Taichung, central Taiwan, and the question is experimental forest station is also located in central Taiwan. That is our study area. I will present our study in 5 parts, from introduction to conclusions. The prediction of species distribution has become a focus in ecology in recent years. With the innovation of remote sensing and GIS, the predictive accuracies and the degree of detail have been promoted. Most of species distribution modeling were worked over the agricultural area or plantation forest. The prediction over the natural and complex forest is very difficult because there are many similar species hard to discriminate and more interactions among species hard to understand completely. With the increasing of species, the environment in the forest will become more complex. They will make the predictions become much harder. Except the environment, when we use different data or methods, they will change the predictive results. Different methods have different characteristics, and they can be used in different kinds of applications. On the other hand, different results can also show more possible status of species distribution. In this study, we want to evaluate the applicability of statistical methods and their effects in a complex forest. The test target species is longleaf chinkpin. I'll call it LLC later. It grows widely in South China and Taiwan. It's a summer tree, and the seeds are an important food source for many animals. The objectives of this study were to evaluate the applicability of 3 statistical methods in the complex forest, and we will also want to explore the difficulty of prediction in complex forest and to understand the possible distribution status of LLC and its potential suitable habitat. Our study area encompasses the Huishan Forest Station in central Taiwan. The tree species over there is very complex. There are more than 1,000 tree species. We took a tree sample from Dongfeng watershed in east of present area and predict the potential habitat to entire study area. The data we used include also photo maps, DEM, and spotlight images, and then derive the altitude, slope, aspect, term position, and vegetation index respectively. The tree samples was acquired from field survey. And we overlay this data and include them into MaxN, SEN, and DT3 models to predict the potential habitat of LLC, and validate the model by using independent samples in final. This map was derived from the DEM we used. The yellow part is the Huishan area. We used the DEM to derive the altitude, slope, and aspect layers, and combined with the region value information that derived from also photo maps to generate the term decision layer. The vegetation index was derived from 2 spotlight images. One was acquired in summer in 2004, and another one was acquired in autumn in 2005. We established the vegetation index based on the principle of the changes in leaves moisture content in different seasons. Shows this equation. The tree samples was taken by using GPS. The errors were below 1 meter. Total tree samples were 123 points. 105 points were from east of Dongfeng watershed. 2/3 of land were used to building the model, and 1/3 of land used in model validation. Other 18 samples were acquired from central and west of study area. They were for evaluating the extrapolability capability of each method. When species increase, the proportion of single species will decrease. Therefore, we use different number of background samples to represent the complexity of forest. The background sample was randomly taken from entire study area. We took 5 times background samples to represent the low biodiversity, and took 100 times background samples to represent the high biodiversity. Now we overlaid these layers and collected biology sample to obtain the information about each factors in the position of LLC. First method we used is MaxEnt. It is based on the entity in thermodynamic and Bayesian statistics. It will find out the probability distribution that occurs most probably in nature. That is the value of maximum entropy. It calculates the maximum probability of presence in every pixel and predict the potential habitat by adapting an appropriate threshold. Second method is SVN. It classifies the data by finding the hyperplan that can discriminate two classes most significantly. If they cannot be split linearly, you will input into a high-dimensional feature space to split two classes linearly. DT is a non-parametric classification technique. It classifies the data by sequentially dividing the dataset into each class with some important variable until classifying completely or reaching the user set limit. In the step of model validation, the approach we used was split sample validation, and we calculate the overall accuracy and the color coefficient to evaluate the accuracies of 3 models. In the result, first table shows the accuracies of 3 models. In the low biodiversity, the kappa value of 3 models were higher than 0.8, means that only 3 models have high predictive power, and the extrapolated power were mediate. Over the high biodiversity, the kappa value of SVN and DT has decreased significantly. In contrast, the MaxEnt can keep the value higher than 0.8. And the extrapolated power of SVN and DT were decreased more significantly, especially on the DT model. This is the predictive habitat of MaxEnt. The dark point are the background samples, and the blue point are the target samples. This map shows that the potential habitat was close to the target samples. All these areas were higher than 1,600 meters. When increasing the background sample to 100 times, the predictive area doesn't change significantly. And the predictions can extend the potential habitat to the west area. The predictive habitat of SVN in low biodiversity was similar to the MaxEnt. It also have high predictive power. But when we add the background sample to 100 times, the predictive area have reduced very significantly. It constrains the potential habitat to very small area, and increasing the omission error. And the prediction cannot extend the predictive habitat to far area like this. And the low biodiversity predictive habitat of DT model was more concentrated than other two methods. And the predictive area were decreased most in high biodiversity over 3 models. And of course, it also cannot extend the habitat to far area. Even though SVN and DT can also be applied in finding the area with much higher probability for species survival, they will be very useful for some applications like the restoration of rare species. And on the other hand, we also can see that the suitable habitat of single species will decrease to a very small area when the complexity of forest is very high. They will make the predictions harder to work. In final, we have some conclusions. All three models have high accuracies in low biodiversity environment. And in the high biodiversity environment, Maxen can keep the accuracy. Maxen was affected by background samples slightly. Therefore, its prediction can remind the area that suitable for target species but occupied by other species. On the other word, that is the potential suitable habitat. And then in contrast, the predictive area of SVN and DT were constrained to very small area in high biodiversity, and thus underestimating the suitable habitat. But on the other hand, they can also be used in finding the highest probability presence area. That may be much closer to the real world. And these two models also show that higher complexity in forest, smaller distribution of single species. In the complex forest, the prediction is very difficult. Not only the environmental complexity that makes it hard to classify each species precisely, but also the interactions among species that's much harder to quantify. Therefore, we will try to incorporate hyperspectral images and LiDAR data into the model to promote the capability of discrimination and prediction of models in future. That's all my presentation. Thanks for your attention.
Okay, thank you. Any questions? Or comments? Okay, please.
I was sorry, did you consider using sort of environmental or climatic variables in your modelling? I appreciate you said it might be hard to get such data over the study area, but things like, say, soil type and water features and things like that.
Okay, we have think about that, but until now we just have the DM and satellite image. Maybe we will try that in future. Yeah. Thank you.
Yeah, follow this question. I also want to ask one question. You see, for the spatial distribution, there are a lot of factors influence that. You only take the DM, right, into account, but that's not enough to use the. You see, if we use the SVM, that is, we keep a lot of mentions, what we can use it as. What that means is that the data is not enough to do that. that method, SVM. We normally use the method from the long yield classification to the near classification. That is some transformation.
I have some standardized in the SBN that I use this for transformation
Yeah.
variable just in the SBN.
But you also use the decision tree. That's also need a lot of rows. This is how to build these trees, and then use these trees, this structure to.
I built the DT tree
Yeah.
using the ISPRS software. Yeah, I just set some parameters in the software.
Just put in
And
parameters.
I use the classification and regression tree to build the tree. Yes.
Okay, thank you. Thank you again.